So go ahead.
Good afternoon, guys. So first of all, thank you so much for allowing us to come and talk to you, although from far away, about our work here at ACCRE with EasyBuild. I'm Davide Vanzo. Most of you probably already know me. I'm an application developer here at ACCRE at Vanderbilt University in Nashville, Tennessee. I'm also one of the EasyBuild maintainers, so that's probably how you have seen me. Here with me today, there is also Eric Appelt, which is one of our senior system administrators. That is one of the two guys that also worked on setting up all the CVMFS file system and moving the stack to it, so that he accepted my invitation to come and join this conf call to talk with me about the work that we did with CVMFS. So Eric, go ahead.
Okay, thank you. Let me move this. Okay, yeah, and just to add a little bit about me with this slide, I was a large collaboration physicist when I was at Vanderbilt before joining ACCRE with the CMS collaboration at the Large Hadron Collider. And then I changed career tracks to go into software engineering and systems administration. And so the point of this is saying that is that previous to this, I was used to having CVMFS around. And so that's where this comes from. The team of the three of us that worked on this was first of all Andrew Mello. He's currently a physicist at Vanderbilt, and he's really in charge of CVMS deployment and synchronization scripting, which we'll describe. Davide already introduced himself, develops and maintains our cluster software stack. And really, I've worked on some of the configuration management for this, testing and benchmarking the system. So when we originally wrote this talk, the target audience was someone who's a user of Lmod and EasyBuild, which I believe is everyone in this room, but somewhat unfamiliar with CVMFS. And the key problem that we encountered at ACCRE and that we're really discussing here is that we want to deploy the software stack that's been built with EasyBuild that uses Lmod to an HPC cluster and really outward from that cluster to the cloud and do that at scale. And to be able to transparently execute users' job on an elastic cloud with the minimal setup and maintenance footprint. So it's not too much of a struggle for us to keep track of this. At ACCRE, our software stack, all the software is installed with only via EasyBuild. The environment modules are managed by Lmod. We have 130 unique software modules visible to users, and several hundred easy config files in its own GitHub repository with several tool chains. So the question we have is how to deploy this. Classically, I think there are two general options. One is to put it on a parallel file system, i.e. NFS, a GPFS, HDFS cluster. At ACCRE, we use GPFS. The good part of this is it's easy to do. You build the software, you put the file on the file system and point the users at it, and there's no additional maintenance required in theory. The downside is this is heavily affected by parallel file system performance. And when there's a problem with when there's heavy write contention, when there's nodes that are leaving the cluster, this can really cause a problem. Additionally, this can be hard to mount on cloud instances. So if you want to burst out into the cloud, and like us, you're using a commercial GPFS file system, that can be pretty much a non-starter. You don't want to add random cloud instances to your file system cluster for security reasons, and there may be licensing costs, so this is difficult. The second option for deploying the stack is to repackage and deploy to the local disks on the nodes. And this means you have to do the extra work to produce RPMs, DEBs, or whatever sort of packaging you're using. So that's a lot of work in scripting for cluster administrators. And if your software stack is large, this may mean you're taking a significant disk requirement on the local nodes themselves. So if you're even using something like diskless nodes, this could be a non-starter. So we've been pretty happy with option one in the past, but the new problems that have come about in the last couple of years that have caused us to rethink this model is one, as I said, trying to burst into the cloud. It's not feasible or legal for us to extend our network file system into cloud instances. And we also have the problem that our software stack contains licensed software and open source software. The licensed software we can't legally put into the cloud, but we can put the open source software, and we would like to do that. Another new problem is graphical interactive use. Traditionally, large-scale computing, our large-scale computing facility has been used for batch processing, but more and more we have research groups that want to run graphical applications directly on compute resources. And software has become available, such as Open On Demand from Ohio State, the Supercomputing Center, which we've started using, which makes it easy for users to request a compute node, create a desktop, and use it in their browser. Once you do that, software startup times become extremely important in a way that they're usually not with batch processing. For example, MATLAB can, depending on write contention, depending on the state of the network file system, take several minutes to start up on a cluster. And the reason for that is it has lots of tiny files. It needs to read them all and reread them all several times. And while in a batch processing, when the users are submitting jobs that will run for several hours, if that software takes 3 minutes or 10 seconds to load, it makes little difference to the user. But when the researcher wants to make plots and use the computing resources in this way, then waiting 3 minutes versus 10 seconds is the difference between usability and having a system that's not considered usable for them. So with those new problems in mind, we really looked at CVMFS. This is used extensively by the high energy physics community. It was developed at CERN as part of the CERN virtual machine project. And what it is a file system that's optimized specifically for deploying software and nothing else. And this is really how the large CERN physics collaborations are able to deploy their custom analysis and event reconstruction software to a variety of clusters, compute clusters around the world. And now what CVMS does is it acts as a read-only file system and using an immutable data model. And this gives it a lot of advantages in terms of distributing software over a general purpose file system. Because the data is immutable, you can get away with some tricks such as content addressing. If two files have the exact same content, then effectively they can be considered the same file, two links to the same file. And you only have to distribute that data once to a compute node. And you really only have to read it once into the system page cache. You can use off-the-shelf technologies. That's a standard fuse mount to create a block device on a Linux system, and everything's distributed using HTTP. And for this, you can use squid proxies to scale up the distribution of the software stack to many systems. So, a little bit of a confession, I used CVMFS for years behind the scenes as a physicist. I never really knew what it was or what it did. I just knew that your software was in the CVMFS directory. I was in charge of writing comprehensive testing of our workflow on the cluster to make sure all of our components worked. And I didn't know what CVMFS was. And that's something to say that CVMS worked really well. It worked quietly and reliably for the CMS collaboration for several years on our system. And I, who was in charge of making sure it worked, never had to do anything. So that was pretty cool. So based on that history and the new challenges we were facing, we decided to go see if we could make CVMFS work, not just for CERN software, but for our own software stack. Now, the basic architecture of CVMFS is you have what's called a stratum 0. This is an authoritative system which new files are written to. This then talks to one or more servers which form a stratum 1. And this is where people will read from the files. This provides redundancy and high availability. If the stratum 0 goes down, you cannot make changes to the file system. You cannot write new files and directories. But as long as there's at least one stratum 1 up, then everyone can, all clients can read files as necessary. Then on top of that, squid proxies are added. These are standard HTTP proxies, and they will just cache stratum 1 data and provide scalability. So if you only have a handful of test machines, you can read directly from the stratum 1 servers, but as you scale out and want to deploy, you could put any number of squid proxies out front and scale to thousands or tens of thousands of machines very easily. So, yeah, go ahead.
Yeah, I'll take over. I take over here. So I think it's worth to also give you an overview of how our stack management pipeline is designed here at ACCRE, because in some ways is one of the approaches. So how do we deploy the software not only on the cluster but also on CVMFS? So we adopt the classical 3 stages development with a dev, QA, and prod. So the dev is let's say our contribution to the EasyBuild community, so to the EasyBuild project. So here is done by a developer like me or like Fenglai or whoever else in our group wants to do it, where we simply develop on our local machine the EasyConfig files, and then we contribute it back to the EasyConfig repositories. The advantage of that is, well, first to contribute back, and then to have a feedback from the EasyBuild community, where sometimes you're building software that you've never seen, and let's try not to reinvent the wheel. Somebody may have good hands on how to avoid issues. Once can you switch to the next one? Once the EasyConfig files are then merged into the EasyBuild EasyConfig repository, we simply have a single QA machine that mimics the cluster, that contains a copy of the cluster stack, and where we pull the dev EasyConfig repository and then extract whatever EasyConfig files we need, and then we can modify them depending on internal needs, and then inject them directly into our own EasyConfigs repository. In this way, we have the flexibility of adapting the installation to our needs, and at the same time to keep constant track of all the changes that we do on EasyConfig files to ensure reproducibility and avoid future errors. The advantage of this is, and also we use issues internally to keep track of problems we had on a software. It was typical before we adopted this system, this way of deploying software, of, oh, the user has this, we're having issues with this software. Oh yeah, I remember I solved that a year ago or something like that, but I don't remember how I did it. So we use issues internally on that repo to keep track of what is going on. So now the EasyConfig files are ready, that are now merged into our internal repository, are ready to be brought into prod. And the way in which we do that is we have a single user for all the admins. So there is a dedicated user to build software on the stack via EasyBuild. So he's the only one that is allowed to use EasyBuild on the cluster. The advantage of this is that it simplifies the stack. They use the file permissions on the stack. So independently on which admin is actually building the software, there is no problem because it's always the same user, so he's the owner. The advantage of the other advantages is that it prevents accidental stack modification. So for example, if I, as myself, build the software on the stack, and then at a certain point I do a pip install and I forget to use the dash user or turn on a virtual environment, the problem is that I would end up polluting the software stack. The other advantage of having a third entity that builds software is that it's easier for user support team to debug and troubleshoot what the users the problems that users have with the stack, because we have the same permission as users with respect to the stack. So it also simplifies that thing. So as Bob the Builder, we then pull from our EasyConfig repository, and we use the Slurm integration in EasyBuild to then launch jobs that build on our debug queue. One of the problems that we have on our cluster is that we have multiple CPU architectures. So in our debug queue, we have multiple nodes of all the different architectures, and we build the software one time on each architecture. So if I'm building something, I'll build it 4 times for the 4 architectures. And the debug queue is connected directly to the stack on GPFS. So here, so the debug nodes can read and write from the stack on GPFS. Once the software is built on GPFS, we have an automatic system developed by Andrew that it nightly syncs GPFS with our CVMFS. And once the sync is done, at that point, both the software is available both for the cluster and for the cloud. So that's in a nutshell how our pipeline works. And
yeah, so the next thing is how easy is this to do? It's actually really easy, because we started with a pipeline, if I'm correct, where we only wrote to GPFS, and then the whole cluster would read it back from GPFS. So in order to make it transparent to the user and have it so that the debug nodes would be looking at the stack as under the GPFS file system, and the rest of the cluster would pull the stack from CVMFS. Basically, all we need to do is some clever symlinking. So what we did is we created a directory ACCRE, and that was just a symlink to the network file system when you're on a build node. And we'd set that symlink to the node architecture depending on the node. So the software that was built against ACCRE would naturally, if you were on a, let's say an Intel Sandy Bridge node, an older node, then that would automatically link to that architecture. And then the software would all just get naturally installed on ACCRE. Now the compute nodes, what you do is our configuration management would simply relink ACCRE to CVMFS, where the directory structure would otherwise look the same, allowing us to also do a fallback to GPFS if the configuration management software noticed that CVMFS is down. And again, the symlink would be set to the node architecture. So this would mean that the software is available in the same place transparently to the user in terms of the file system hierarchy, but it's really being served on CVMFS or GPFS depending on where you are on the cluster. So just to show you an example, here I am on a standard node. And I can look at some symlinks, ACCRE common and ACCRE arch. So ACCRE arch is a symbolic link to a system within CVMFS. We use the Oasis server on the Open Science Grid to serve our open source software, and you can see it links into a directory which has Sandy Bridge in the path, as this is a Sandy Bridge machine. We have a separate common directory, which we didn't mention, serves for certain binary distributed software where it doesn't make sense to compile different versions on the different architectures. That all goes to the same directory. Okay, now if I go to one of our debug nodes, and I look at the symlink ACCRE common points to GPFS 22 ACCRE common. So if you're the builder user, you can then write and update that directory, and overnight that will be synchronized so that the other nodes see the exact same thing. Again, if I look at ACCRE Arch, this points to the internal, the GPFS read-write file system, but here you can see we're linking to the Skylake architecture. The other issue we had to solve in distributing this is differentiating between open source software and licensed software. For the open source software, we actually didn't need to set up our own CVMFS server, as we're part of the Open Science Grid, so we were able to use their OASIS system, which provides this as a service to other clusters. And again, what we do is in GPFS, everything works normally. All software is built in the same to the same directories, and then we can use symlinks on CVMFS to separate out the private and the public software. So the module directories in CVMFS will be in the nightly sync. We just flag certain directories as private modules, and those become symlinks to another location. If you're out on the cloud, these private links will be ignored by Lmod if they're broken. So all the licensed software we host on a completely separate CVMFS instance. This is only available on the internal network. There's no external link. Oh, question? Or?
Yeah. How do you solve the problems with some software that are resolving those symlinks from ACCRE Common or ACCRE Arc down to the GPFS file system into their bash files or whatever?
The symlinks are on the top of the directories, so
yeah, but some softwares, when they install, do symlink resolution and puts the actual path into their scripts. Lots of software do that.
Yeah, no, I see what you mean. That's a good question. As of now, we haven't hit that issue yet, so it's kind of...
You haven't?
No.
Have you looked closely?
Well, everything seems to work when the image will. No, I mean, yeah, that's definitely a good point. It's definitely something that we haven't hit yet. So probably we're just lucky.
Yeah. So going on with that good luck. So I could show you too this symlink. If I take a package like if I take an open source package, Anaconda 3, oops. Okay. This is a directory on our build node. But if I take one of our licensed software modules, like MATLAB, okay, on the build node, these are both directories. Now, if I exit the build node and go back to the cluster, you can see that Anaconda 3 is still a directory. But if I look at the licensed software, oops, this is a symbolic link, and it goes to a different CVMS server, which is our private one. So what happens is, if we go to a cloud instance, MATLAB will just appear to them as a broken link, and it will be ignored completely by Lmod. Well, if you're on the cluster, you'll actually see that when you run a module avail command. So here's a big chart of our overall distribution model. The internal, everything highlighted in blue is something internal and on premises to ACCRE. So for ACCRE, we have our GPFS file system, and nightly that gets synced to our private Stratum 0 servers. And then that can go forward through an internal architecture where we can set up as many Stratum 1 or Squid proxies as we want inside the internal networks. Cluster nodes can then read from that. The open source software will send out to the Open Science Grid OASIS server. Now, if you're not an Open Science Grid member, you could also set up a separate server internally to be your Stratum 0. Let's see, sorry about the typo there. And then that architecture has Stratum 1s and external squid caches. So what happens is that our internal squid caches are reading from both the internal and the OSG Stratum 1 and collecting together all of the software. If you're on an external user workstation or a cloud instance, you could then read from the OSG, an external squid cache that just reads from those Stratum 1s and just gives you the open source software. Okay. And we have a little demo for the cloud instance. So I've created a cloud in AWS I've created an instance in AWS a couple minutes ago before I started this presentation. I haven't logged into it yet, so I'm gonna do that now. And what I'll do is I'll run a simple script to enable Lmod and connect it to our open source software stack. Oh. Okay. Now, I've never logged into this, just to show you. I've never logged into this before. Oh. And this is a stock instance of CentOS 7 from the AWS collection. So this is right off the shelf. So I'm going to grab this simple script. And then this could be properly, from this script, you could create your own AWS image or containerize these instructions. So I'll just run it. And this will set up, and in just a minute or two here, set up and get the software stack ready to go on this new image. Any questions while we're installing software?
No questions so far.
Okay.
So now we're just populating an entirely empty environment. That's right. Yeah, this is so this is just demonstrating that this is pretty simple and fast. You can this is a stock core CentOS 7 image. Okay, so now everything's installed. I should be able to log out, log back in, and type module avail. And then again, this is going to have to do an initial read from CVMFS and populate the internal cache. And there we go. So I can see some compilers and binary distributed software, and I'm ready to go. So I can load whatever module I want. And I can start doing work. What's really nice about this, in my opinion, is that a researcher can create a container that links into CVMFS and that sort of dynamically gets updates to all their scientific software stack in a cloud image.
Whereas if you were to try to put all of this software into one Docker image, that would be kind of a pain, and you'd have to do updates. This sort of short circuits that step.
Just to add a similar use case, another one is, for example, we have a few users that they have some pipelines that are half on their local workstations and half on the clusters. So the problem for them is how to have a consistent software stack that allows them to seamlessly move the part of their pipeline from the workstation to the cluster and vice versa. So one of the things that we are doing now is, for example, to allow users, obviously with our supervision, to allow users to mount the part of our stack, so the GCC, the FOSS part of our stack, directly into their workstations. In that way, they can build the software, and they can have the same software on both sides and build on top of the same stack.
Yeah, so this is an exciting new way we can distribute. So the other issue is with this issue of interactive startup time. And here's where we really had a problem. With the cold cache, and this is one data point that I'm showing right now. This shows the startup time of some packages. Python with loading, I think had NumPy and scikit, trying to just import those modules and load Python, trying to load MATLAB, and trying to load R and just run an empty script. When we use the GPFS file system, which again, this is on a regular day, there's lots of workflows going on. You know, the file system is under some regular stress. You could see it could take as many as 90 seconds to load up all the Python modules, several minutes to load MATLAB. And when we switched over to CVMFS, those load times really shot down by an order of magnitude. Now, once the cache is warmed, once the data for those files is on the compute node, loading this software, then the difference doesn't make as much. It doesn't matter so much. In fact, GPFS may be a little faster here, due to how it uses user space caching versus the fuse mount for CVMFS. But in terms of the user experience, this is pretty similar. And just to demonstrate what our users are doing is we have an open on-demand system, which gives users in-browser desktops that they can launch and ask for. Oops, I should clean this up. And a user might want to use this desktop to let's say, load and run MATLAB. And here's the step where we really had a lot of users' complaints. If there were any significant difficulties or stress on the file system, this could take several minutes. And again, with the CVMFS, all the little files that go into loading MATLAB can be put together as a block, shipped over HTTP. And you know, if there are multiple files that have the same content, these can also be read ones. And so this will show up for the user in less than a minute pretty reliably now, which is still slow for any application these days, but it's a lot better than when you're trying to load MATLAB over a read-write file system. And there we go. Okay. Oh, and so we did that. So the basic conclusion before we go to questions and further discussion is basically we found this is a reliable and reasonably simple method to distribute scientific software. that we can easily extend out to the cloud or to other nodes in our researchers' work groups that we don't want to connect for whatever reason to our cluster file system. And it's also very nicely suitable for interactive use.
Thank you very much.
And
yeah, go ahead.
No, I was just saying that that's also, if you have any questions or anything on that side, we are happy to help, to answer.
You said you have dedicated build nodes?
Correct.
How large is that system?
What do you mean, how much?
Or how few users do you have?
No, it's just so we currently have 1, 2, 3, 4, 5 CPU architectures. Well, also because we have one that has GPUs. So we have four GPU architectures. We have 4 nodes that are our debug queue. So what happens is that I understand your point in a sense of, well, you know, just dedicating nodes just for building is kind of a waste of money and cycles. So the way in order to you know, use them as much as possible is to make them available through our debug queue on the cluster. So they are both accessible by the users for debug purposes and at the same time available for us for building. That does not slow too much our process because the maximum job that can be launched by users on the debug queue is 30 minutes. So, you know, if we have to build a software, worst case scenario, we have to wait 30 minutes. And that's the way in which I justified to our managers how to give me 4 nodes, 1 per architecture.
And if that's a problem with virtualization, you could reserve, you know, create VMs with just 2 cores on it, 1 or 2 cores on a node, and release the others for general purpose computing too.
Yeah.
Yeah. Okay. Any other questions for Davide and?
Hi, this is John Day. I'm curious about how you are using Squid in AWS. Is that a standard image that you're getting from Amazon, or?
Oh no, the Squid servers are dedicated machines on premises.
So that's on-prem, and you have a dedicated connection to the AWS cloud.
So the Squids, so for the software that so we have a compute node on the cloud here, basically, that can access the software stack. It's using the public-facing Squid proxy. And that Squid proxy, we could have our own. This one's actually hosted by the Open Science Grid. And so literally anyone in the world can talk to the Squid proxy. We could conceivably make restrictions based on IP address or, you know, other qualifications. But yeah, as it stands, this is basically exportable to everyone.
Thank you.
So yeah, so the cloud node doesn't need any specific credentials to talk to the Squid server. We just stand it up, and it immediately begins communicating.
Okay, great. Thanks very much. Let's give a little.
Thank you, guys.
Okay, I'll stop the streaming briefly, so we'll set up the next talk.